and welcome to DynamicsCon 2022. This particular session is Machine Learning in 40 Minutes. My name is Michael Sims. I am the Vice President of Digital Advisory for Columbus Global. You can see my information here. Please contact me on LinkedIn, or you can reach me at my email, which is listed below. I'd like to thank DynamicsCon for creating this forum for everyone to get together and share content and try to learn. There will be a live Q&A at the end of this session, so please write down your questions and I will answer them after the session. The agenda for today: data science, machine learning basics, data, algorithms, building a predictive model, interpreting results, and finally the questions. Start off with data science. In machine learning, there are several roles that are required to make good models and to provide value to companies that use these models. At the top of the list here we have data scientist. This particular individual is a highly educated and skilled person who can solve complex data problems by employing deep expertise in scientific disciplines. These include mathematics, statistics, and/or computer science. A data professional is a skilled person who creates or maintains data systems, data solutions, or implements predictive modeling. Some of these roles include database administrator, database developer, or BI developer. You might also hear the term data engineer. A software developer is a skilled person who designs and develops programming logic and who can apply machine learning to integrate predictive functionality into applications. These roles can be with one person in your organization, or you can have an entire team where these roles are separated. Let's dig down a little bit more into data science. Typically, the data scientists that are in the world right now are in computer science, or they have a very extensive background in statistics. A lot of times they have both of those. They've worked in the analytics space and they've continued to build up their prowess in computer science with the tools as they have evolved. The best definition that I could find is that data science is a multidisciplinary blend of data inference, algorithm development, and technology in order to solve analytically complex problems. And this came from Data Jobs just recently. So why do we care about data science? The main reason here is explosive data growth. As you'll see in the next slide, data has just exploded at an exponential pace over the past decade. What we're finding is that data is increasingly cheap as well as being ubiquitous. Much of the data that we deal with now is unstructured or semi-structured, and there are constantly new technologies emerging. One of the drivers behind this is analytics. Analytics itself is driving a digital transformation in the space. What we're seeing is many companies are moving to the cloud at a record pace now, and analytics is driving that move. Another thing that we're seeing with these new technologies is that AI is the new normal. And the reason we see that is because of things like IoT, machine learning, and analytics. If you're not familiar, IoT is basically little sensors that exist on machines and provide information about those machines. A number of projects that I've been involved with have thousands of these IoT sensors. Getting that data and finding the correct tags, is what they're called, to provide any type of predictive inference is really the trick, and that requires working with the business to determine those tags, the correct tags. Machine learning helps to analyze that information and create predictions based on historical information. Analytics helps us to look at that data in either a graphical form or some type of a reporting structure that we're comfortable with. This slide was pulled about a year ago, and you can see where the prediction is with data by the year 2025. If you look back just a few years ago, say 2016, we had less than 20 zettabytes of data in the global data sphere, is what they call it. In a couple of short years here, we will be at 175 zettabytes. I referred to structured and unstructured data. Structured data, like many of us are used to with systems like Dynamics AX or D365, is a relational database. We typically take that relational data, which is very highly normalized, and we invert it or build star schema and create a data warehouse out of it. However, a lot of data has moved into an unstructured or semi-structured context. And what you see now is that a lot of our data now comes in video form or in text form, images, sound, and video, or some other formats. This type of data is notoriously difficult to search on. A lot of the data that we see now is created by machines. Think about EDI, for instance. Just a few years ago, we were typically typing in our sales information. Now EDI has automated much of that. So what is a good data scientist? A data scientist really combines a lot of different disciplines. Whereas you might think of an analyst as being very strong in business administration and digging into data through data exploration, analysis, and insight, a data scientist builds upon that by adding advanced algorithms and machine learning as well as data product engineering. The specialty role within data science is very focused on math, technology, and business acumen. Data scientists work at the raw database level to derive insights and build that data product. So what skills are necessary for data science? You really need to have at least these three areas and have significant comfort with mathematics, technology, and business strategy and or business knowledge, process knowledge specifically. The intersection of all three of these areas is typically what we consider data science. Invariably, though, data scientists are stronger in one or two of these areas and might need help from other members of the business community. So let's talk about machine learning basics. Machine learning has two broad groupings, and those groupings are to make predictions or to have pattern discovery. When you're making a prediction, you build a model, you train that model, and then iteratively you process the model and it increasingly gets more and more accurate. The more data you can put through a model, the more accurate you're going to be in the long run. The other broad grouping is pattern discovery, and this allows algorithms to detect natural groupings of data. We also can employ clustering techniques in order to find interactions between two or more variables. There are other categories such as collaborative filtering and contextual bandits, but primarily most of the machine learning that is currently being done is around prediction and or discovery. Machine learning itself is a scientific discipline that explores the construction and study of algorithms that can learn from data. And you're going to see here in the next slide graphically what we call supervised learning and unsupervised learning. With supervised learning, we know what you're trying to predict, and we use techniques such as regression and or classification to figure that information out. With unsupervised learning, in general, we kind of know what we're looking for, but we might want the system to assist us, so we will use something called clustering and or anomaly detection. If you look at this graphically, starting from the left with regression, you can see that we have a multivariate regression model here, and that shows a cluster of data around a line. That green line shows the actual trend, of that result. With classification, you can see there's an actual class boundary surrounding the most frequently used services in this particular case. In the unsupervised learning column, you'll see that there's clustering and anomaly detection. With clustering, you can see that there are three distinct groups here that we would want to try to focus our efforts on. With anomaly detection, we can see if there is some type of outlying value that might not be where we would need it. Think of this as a statistical process control that's gone out of control, but it's in a multivariate type of an environment instead of just two dimensions. So for IT professionals, machine learning is one of the most popular fields in computer science, and it might be one of the most feared by our developers. And this is probably due to the fact that we're concerned that, hey, we really need to have some type of deep mathematical expertise. But machine learning really has two different disciplines. It has machine learning and applied machine learning. With applied machine learning, you can actually use tools that are pre-made and just wire them together to create predictions and or clustering and so forth, like you saw in the previous couple of slides. And you can integrate predictive functionality into application experiences. A lot of what we're seeing now in the Power Platform specifically has automated this process. Some of the business scenarios that machine learning could be applied to are ad targeting, churn analysis, image detection, and so forth. I'm not going to go through all of these, but think of it this way. If you have gone on a trip somewhere and your credit card has gotten frozen for whatever reason, you get a phone call from your credit card company and they say, "Did you make this purchase?" That was a fraud detection algorithm that the credit card companies have built out using machine learning. And they will freeze your account rather than let someone other than you potentially spend on your credit card. Yes, it's annoying, but it's really kind of a good thing to have. So some of the machine learning challenges, if you look at the circle there, if you start at the top, there's a lot of competition around machine learning. And this is even between the major platforms and also in open source. So if you are looking out there for some open source type of machine learning and statistical analysis tools, you can look at something called KINME, K-I-N-M-E. If you want to look at the Azure Machine Learning, there's an entire studio out there, and I'm going to show you that in a little bit. But the competition and the desire for many companies to get into this space is just enormous. There's also strategic change. How do we determine if this is strategic for our company? How do we make sure that it is adaptable in the long term and the short term to meet our business needs? There are a lot of buzzwords around machine learning, and those buzzwords might be very important or they might change. Knowing which buzzwords are important can be a challenge here. And there are new markets. How do we apply machine learning to help with those new markets and build those things out? Some of the other challenges is that we traditionally consider machine learning to be an expensive tool to learn and to get integrated into our business. And a lot of times we look at those projects as being very, very expensive. We might think that we have isolated data, and how do we ingest that data properly? And we might not have a data lake to feed off of, or we might not have access to the particular applications, so that data might be very difficult to get to. We might have tool chaos, and that kind of gets back to the whole high competition piece of this slide, where we have all of these different tools and all of these different sources, so there's a lot of different compatibility issues that we have to worry about. And there is the complexity part of the entire machine learning process. So my best recommendation there is keep it simple to start. Don't build a 500 parameter model when 5 variables will get you 80% of what you need. Start with the 5 variables and build where you can build, where it makes sense to build upon. The traditional approach with machine learning has been a little bit of guessing, some rules of thumb, and some trial and error. With the way I'm going to show you with Azure Machine Learning Studio, you can actually run several experiments simultaneously to determine which algorithms work the best for you. The consequences of these machine learning challenges are we're losing opportunities potentially, and sometimes it is expensive to make these operational mistakes. So how does Azure Machine Learning work? I'm not going to go through this entire slide in complete detail. The next slide is actually a little bit simpler, but this gives you an idea that you start with some type of Azure portal or Machine Learning Studio, and you create your workspace and your storage accounts. You get your data from a variety of sources or one source, depending on what you're going to use machine learning for. You run that ML API service in Application Developer and test those models, build those models out, iteratively work the models, and then you can deploy them into web apps, mobile apps, streaming, or Power BI. The simpler model, the basic workflow, is that we're going to collect some data, and that data can be from a variety of different sources. It can be blobs or tables, it can be Hadoop, it can be relational, or it can be from anything that's unstructured or semi-structured like a data lake. We run it through a machine learning service, we build some type of a model, we train those models, and then we output a web service that can be run and scheduled, and that scheduling can be as often or as infrequent as you need it to. And then we can embed that machine learning model into our apps or into our devices and make it work for us. So the Azure Machine Learning Studio is really a platform for us to graphically build and deploy experiments. If you're comfortable with SQL Server Integration Services or Azure Data Factory, any of those types of tools, they're very graphical. This is similar in that respect. It allows for rapid experiment composition. There are over 100 easily configured models for data prep, training, and evaluation. There's extensibility through R and Python, and it allows for serverless training and deployment. And some numbers are there's been hundreds of thousands of models deployed, and they've been serving billions of requests. As you can see in this particular screenshot, along the left-hand side, we have our very familiar Microsoft icon groupings where you can have several different pieces of the machine learning modeling available to you. I'm going to show you this in a little bit when we get into the demo. So characteristics of a machine learning experiment is that you need at least one data set and one module. Data sets can be connected to one or more modules. Modules can be connected to either data sets or other modules. All input ports for modules must have some connection to the data flow, and all required parameters for each module must be set. Some of the more common use cases are demand forecasting, profitability analysis, process optimization, preventative maintenance, pricing optimization, customer churn, and you can use your imagination. One of the most common things that I have seen machine learning used for is some type of demand forecasting. As anybody that has used AX or D365 knows, demand forecasting within that particular tool is challenging at best. Machine learning allows for you to do a much more in-depth demand forecasting than you would be able to do within the AX or D365 tool set itself, because you can harness the power of Azure and really up resources to meet the needs of something as challenging as demand forecasting. Another thing that you might want to consider in this day and age of having a very limited worker source, if you will, is instead of customer churn, look at worker churn. How can you predict if an employee is going to stay with your company or is maybe at risk of going to another organization? You can model that and use machine learning to determine how best to approach employees in your own organization. Okay, I'm going to do a demo now, so I'm going to switch screens. This is Machine Learning Studio in Azure. And as you can see here, I have projects, experiments, web services, data sets, trained models, and settings. I'm not going to go through all of these in the interest of time, but I would like to highlight a couple of different areas here. The first one is experiments. You can see, once it comes up, that I have about a dozen experiments here that I've worked through at various different times in this particular account. I have some forecasting models, some demand estimation, and those types of things. If you look at web services here, I only have one that I've really deployed to a web service under this account. With data sets, you can see the data sets that I have brought in for the different experiments. So the first experiment that I would like to look at is the automobile price prediction experiment. If you look here along the left-hand side, now that I've moved into the experiments, I have a whole suite of icons available. Data sets, trained models, transforms, and so on. If you look at the data sets, for instance, you have samples and you have your own data sets that you have access to or you've imported. Again, in the interest of time, I'm not going to go through a connection. I'm assuming that most people know how to connect to different data sources that are in their organization. But let's take a look at, for instance, adult census income and the airport data set. I'm just going to drag those in here. We can take a look real quick at the data set by either downloading it and or visualizing it. I'm going to choose visualization. And you can see that we have age, work class, not sure what that particular field is, education, education number that they've assigned to the verbal on the education, and so forth and so on across the data set. If you start clicking on particular columns within the data set, you're going to get statistics and visualizations over here that represent that particular column. So if I go and I look at work class, the huge dominant portion of this particular data set, 70% of them, in fact, are privately employed. If I look at education, I have high school graduate at 32%, and I have some college at 22%. So you can see all of this data has a fairly good distribution. It's not completely skewed towards one or the other, so it's a fairly good adult census. Now, it's obviously not the entire census of the country or even a state, but it's a fairly decent data set. This particular data set I pulled to show a more limited data set in that we only have a few columns here. And so you want to be careful as you're going through and looking at your different data sets. For instance, if you're focusing on a specific area of the country, that's what you would expect. If you were focusing on the entire country and you only had these states in here, then your data is somewhat non-representative of the entire country. So let me delete these because they are not part of this particular experiment. Go through this a little bit here. So I import data, my raw data from my price data, and I'm going to show what that looks like real quick. And this shows make, fuel type, aspiration, number of doors, body type, and so forth and so on. You can see I have a number of columns here, even to the right, so I probably have 25 or 30 columns here. And if I look, for instance, at body style, I have mostly sedans, a couple of hatchbacks, and so forth. Width is just going to be, I think this is in inches. Height, same type of thing. So I have a fairly good representative, almost normal curve here. If you look down here and select columns, this will tell you what columns were actually selected. I'm not going to go through building this out. Clean missing data, if I have a 0, for instance, I want to remove the entire row. And then you could go through and set up rules and then do more selections as you see fit with your particular experiment that you need to run. I'm going to run this experiment now. It's only going to take a few seconds. Once I get all green, I am good to go. So everything is green. So that took, I don't know, what, 5 or 6 seconds, I think. So the first thing we're going to do is we're going to look at the scored model, and we're going to visualize that. What does that mean? Okay, so this scores the 9 columns that we chose and says, okay, what do those numbers look like? And I scored my labels. And basically the scores are going to be what determines my price. And if I go down here, I look, I see I have a mean, a median, a min, and a max, a standard deviation, and how many unique values. I have 46, which is a fairly small number here. And if I look at my evaluation results, I can see that I have a coefficient of determination of 0.91, a root mean squared error of 2456.98, and a relative absolute error of 0.27. I'm going to explain what these mean here in a second, but kind of jot those down in your mind. If you look back at this data set here and go to visualize, it's not letting me do it. So for the automobile price prediction, you can see with these variables, make, body style, and so forth, the scored labels give me an estimate of what the price of that vehicle should be. So expectation-wise, for instance, I would expect a Mercedes to be more expensive than a Dodge. So if you look at, let me find the Mercedes down here, Mercedes-Benz, $35,000 almost, right there. And if I look here up at a Dodge at $6,300, the hatchback, that more than meets my expectations. Now, is that accurate based on the information that I have with a small sample size? Yes, I would say that it is. Now, again, if you look at the evaluation of the model, I have a very high coefficient of determination at 0.9, and my relative absolute error is pretty low at 0.27. All right, so let's talk about data. If you've ever been to any of my sessions, you know that I talk about it's all about the data. And as you start dealing with different systems that are more and more interconnected, you start seeing that it is truly all about the data. So your customer insights is going to be some combination of different systems that you have in your organization. And you can have anything from your ERP to website visits to orders that are coming in through CRM and getting processed into some other system, maybe a 3PL, and then end up back in your ERP system. You can have a management information system that does something like engineering. You can have IoT information. Even LinkedIn, social media, email, all of those different things can lead to different insights in your data. And the complete customer insight that you might be looking for might be some combination of more than one and maybe more than a half dozen different data sources. So how do I get the data is really the important part. And a lot of people are getting very good at doing this, but there are, as many different types of ways to get data as there are sources out there. So you can use a web URL, API using HTTP. You can use Hadoop. There's Azure Blob Storage, Azure Tables, SQL. There's also Azure Synapse now that's coming out that has a lot of this functionality built in. You can actually run machine learning models from within Synapse. You have on-premise SQL Server databases. You have on-premise AS400s. You have data feed providers, which is usually an OData, in D365 right now, for instance. You have Azure Cosmos DB as well. So you have all these different ways to get data and to store data. One of the key things you need to understand as you're building these projects out is you really need to look at the quality of the data, and that requires some assessment and exploration. Am I getting the right kind of data? Am I getting the right quantity of data? So for instance, in that car pricing, we really only had 46 data points, so it's relatively small. We would want hundreds or potentially thousands of data points to get a more accurate representation of that particular experiment. We want the right quality of data, so we can go crazy with data quality and make sure that it's 100% accurate, but usually you can get close, and your data quality, as long as it meets the standards for all of your code tables and your master data and your transactional data is complete, then you're getting the right quality. You want to look at how your data is distributed as well. Make sure that we don't have skewed data. Make sure that we have representative data of the data population in the whole. Are there outliers in that data? If so, how do you treat those outliers? Do you take them out, or do you keep them in because they are part of the data set? Make sure that you eliminate duplicate records, and make sure that as much as possible you're cleaning up your missing data. So this slide generally gets a little bit of attention. When I say the data is the data, that is because a lot of people, when I'm working with them, have decided for whatever reason that their reporting system is the authoritative source of truth. In the cases of a lot of ERPs, that should not be the case. You should have your ERP system, your information systems, whether that be an engineering system or whatever, as the source of the data. That should be the source of the truth in this case. Data munging and wrangling and data cleansing part of it can be a significant effort. We want to pre-process our data and prepare our data appropriate. Again, make sure that the right level of cleansing, standardization, and scrubbing are applied. And where necessary, we want to transform data. We don't want to change data necessarily, but we want to make sure that it maps correctly. So a good example of that is if item numbers have changed, we want to make sure that we're getting the right item number for the new system, and we don't have potentially duplicate data just with a different ID. And we want to make sure we have the adequate and sufficient amount of data to make whatever type of prediction we're going to make. And the reason is because bad data leads to incorrect analysis, invalid insights, wrong decisions, and poor outcomes, and it really becomes kind of a self-fulfilling prophecy, and it's kind of a circle of doom there. So with data wrangling, all of these things are available. You can ingest your data, explore it. You can try to shape your data, see if there's any obvious ways that we can clean it up and transform that data from being relatively unclean to relatively clean, and then actually look for missing values, formats, outliers, and so forth. We want to also, where necessary, augment the data by using aggregate data sources and or fuzzy and exact matches. So what about scale? Well, when you start getting into larger scale data sets, you're going to want to make sure that you have enough processing power to handle the large data sets. You're going to want to make sure that the number of experiments that you have doesn't tax the system, because you want to get the correct values that you need, and you shouldn't be running tons and tons of experiments if you don't need to. And then you need to be concerned about what tool do I use. One of the big concerns that we had internally is I want to use R, and the other person said, well, I want to use Spark. Okay, use R or use Spark. You can work with both of those. But you need to understand where you can use one as an advantageous piece of the experiment, and where another one might be more appropriate. Again, wrangling data, I'll bring that up again, and deploying and monitoring your data. You'll want to ensure that you're keeping an eye on that. So let's talk about algorithms. What question are we asking for the experiment? So are we looking at a classification question? Is it A or B? We're looking for is something weird. In other words, is it an outlier? Is it an anomaly? We want to know how much or how many. That would be where we'd bring regression in. How is that data organized? So is it clustered? And what should I do next? And that's more of a reinforcement learning question. And this is from Azure. This is kind of your machine learning algorithm cheat sheet. And based on what you want to do, this is a good starting point. And you can say, for instance, I want to predict between two categories, and then I go into a two-class classification over on the right middle. If I want to predict values, I can go over to the regression algorithms in the bottom left. And you can see there's half a dozen different regression algorithms. So which algorithm do I use? Well, you start with the cheat sheet, and then it depends on the question to be answered, the type of data, and the amount of data that you have, and how much time do you have? How much time is it going to take for you to build these experiments and get the data that you need and run them through and train them? And then what do you want to do with that answer? So with classification, you can see that there are basically a dozen or so different types of classifications. If you look, for instance, at two-class boosted decision tree, it's an ensemble learning method. It's the easiest method to get top performance. It is a bit of a memory hog, though, so it might not be able to handle your very large data sets, or you might have to provision more resources into your Azure stack to handle it. The use cases in this case are direct marketing to gauge customer propensity to buy, credit card risk, and so forth. Regression, how much or how many? In this case, let's talk about Poisson regression. This is used to model counts. The use cases for that are number of colds associated with airplane flights, estimating the number of emergency service calls during an event, and projecting the number of customer inquiries subsequent to a promotion. Clustering, k-means clustering is the main one that we see out there. Use cases there is detecting abnormal data, clustering of text documents, analysis of data prior to other methods. So I'm going to run a predictive model. So here is my compare regressors predictive model. And you can see, if I blow this up just a little bit, that I have my data source at the top here, of course. I'm importing my data, editing my metadata. You can see over here that I have done some things with the different columns, splitting the data out so that I have data going to all of my different models. And then if I start like over here with the Bayesian linear regression, look at trained data model, you can see that it's just going through and showing the specific properties of each of those. If I score this model, visualize that data set, I can see that I have a variety of different statistics that come across here. I'm going to show you really the end result here. This is kind of the scored data sheet for that particular model. So let me zoom back out, and we're going to visualize this. The purpose of this entire that entire widget here is to get what the different algorithms look like from these particular different statistics. And really what I'm looking for here is I want the lowest value of error. So the closest value that I get for error is the best in this case. And as you're going to see here, the boosted decision tree regression is the lowest in all 5 of these different categories. Now if I look at my mean absolute error, I can see that I'm pretty consistent here. If I want to compare them, I have that option available to me as well. And you can see that there is a correlation with a lot of these. So how do I improve the models? You're going to want to iterate these. You're going to want to basically do a POC, start small with your data, change the features used in the prediction, modify the in this case, linear regression algorithm properties or the other regression algorithm properties. And you can try a different algorithm or do what I did and add multiple machine learning algorithms and compare using the evaluate model module, which I showed you at the end there. So let's get to the really important part here, which is interpreting the results. So if you remember back when we did the automobile test, we had an actual value, the known value here, which was price, and we had the predicted values. Now the difference between those in aggregate is going to be our errors. And in this case, our error was 0.27 relative absolute error, and our coefficient of determination was 0.91. What does that mean? Now, I'm not going to go through every one of these in this particular case, but if we look at The mean absolute error is the average of the absolute errors. An error is the difference between the predicted value and the actual value. So the closer we are to that actual value, the lower this error is going to be. So the interpretation of this is that for each error statistic, smaller is better. Now for the coefficient of determination, the closer the value is to 1, the better the prediction. So if we could get that coefficient of determination into the mid-9s or the high 9s, we would be much more closer and better predictive. So to compare regressors, if you remember correctly, we went through these different algorithms. I realize I went through it fast, but there's the model again, just for reference. And the results were that we had these different errors. Boosted decision tree regression had the lowest errors among all 5 of these different algorithms. I hope that during this presentation you have entered questions into the chat window, and now I can answer those questions for you. So Bobby, let me start with your question first. First off, challenge accepted. I think I did it in 38 minutes instead of 46. Of course, it was a very, very high level. There's a lot more to this topic than of course I covered in this presentation. It was originally a 90-minute presentation that I had to break down, and even 90 minutes is just a scratching the surface. Investments as far as taking advantage of machine learning in a D365 environment, I think the initial investment is to get export to data lake configured in D365 so that you can get the data actually out of the system that you need for your experiments and that you need for any type of either augmented or artificial intelligence that you would want to build upon your D365. And that also allows you to mash data from other systems together, of course. Is there an established ROI for employing machine learning in an organization? That's an excellent question, and I don't honestly have an answer for that one. I think ROI is usually why we get involved with some of these experiments. I have a MS Dynamics World webinar that I've done on enterprise analytics that uses machine learning to consolidate data from IoT. I kind of alluded to that in the presentation. And multiple data sources, of course, feeding into it, Oracle, IoT, and some other data sources as well. Their ROI is reducing their breakage, which was causing them significant costs. And also they were able to change their production parameters much, much quicker as a result of having this system in place. We built it out as a POC originally. We are still waiting for them to get completely fired up after COVID so that we can deploy this throughout the rest of their organization. But from our perspective, the good news is they referred us to a sister company, so we're going to get involved with them as well. Ludwig, you asked about, is it really possible to use machine learning for employee and customer churn? Look at it this way. If you're going to do product forecasting, for example, or demand forecasting, you have a lot of known variables and a lot of known parameters. However, you have a lot of unknowns that are going to come up as a result of either going into new markets or changing business conditions or any of a number of other conditions that can happen. So you model it, you refine the model, you keep adding data to it, and you refine the model some more. That's the iterative process that I was talking about. It is possible to get better. I don't think it's 100% possible with machine learning to say this employee is going to stay with us or this employee is going to leave us. Can I post the link to the cheat sheet? I do. Sheila, if you would be so kind as to email me, anyone, I think you can probably Google it, but the one that I found, I think I just put in Microsoft Machine Learning cheat sheet and it popped up. If you can't find it, email me and I would be glad to provide it to you. Bruce, don't get too green on me, buddy. I always try to treat data well. Marie, thank you. Thank you, Anna. I think Bobby is trying to help me out here. Thank you, Bobby. Hope to see you soon in person. It's been a while. Sheila, what would be my recommendation for going deeper and learning more about machine learning? I would start with the Microsoft Docs. There's a bunch of really good stuff out there. Be careful getting too deep too fast. You want to make sure you get the foundation and the good basic structure of what's going on here. And you can do a lot with a little. So I'm not trying to shy you away from this by any means at all. But if you're going to get deep into machine learning, make sure you have a good understanding of statistics and what the algorithms are actually doing, because the algorithms make assumptions and they build out a lot of code in them, especially if you use Machine Learning Studio, that you're going to have to eventually maybe have to explain that those assumptions and why that code's doing what it's doing. Bobby, yes, I do. Do I recommend organizations start the process of establishing one source of data and an in-house data curator ward? It's all about the data for me. Bobby, I've been in this space for over 2 decades in AX, now going into D365, but it's always been on the back end with data and data warehousing and now machine learning and all of these other things. One source of data is very difficult to achieve, and it is something, though, if you're going to build a good solid analytics platform on, or you're going to build out something for machine learning, you want to have not only that analytics platform for the data that's already happened and make sure that the data is curated properly, but you also have a master data management strategy to manage your items and your master data, your customers, vendors, all of those things that we really don't worry about until we do an upgrade. So having that one source of data and a curator or a ward, that should be on the business. That should not be a technical process. I mean, you have the technical folks in IT help you with it, but who actually owns that should be in the business. And Bobby found the link. Thank you. Thank you, Sheila. So any other questions? Wait a couple of minutes here. Thanks for being on this presentation. I really enjoyed it. If you have any questions on this, please reach out to me. You have my email.